Hi everybody, welcome to Dr. Manny's YouTube Learn Shops again. This session will deal with part 2, estimation in hypothesis testing as an element related to inferential statistics. The learning objectives for this session are to explain estimation, discuss point estimates, confidence levels and confidence intervals, and calculate and interpret confidence intervals. The definition of estimation basically is that in statistics it's concerned with inference about the numerical value of an unknown population from an incomplete data such as a sample. Estimating population parameters from sample parameters is one of the major applications for inferential statistics. Estimations lead to inferences. So you can have a population of Malaysians and you can make inferences about that population from a sample of the population. And basically what it means is that from a population you try and reach conclusions about the population when you take a subset sample of that population. Key terms that we need to consider for this session are point estimate, confidence interval and confidence level. So a point estimate is a sample statistic used to estimate the exact value of a population parameter. The confidence interval is a range of values defined by the confidence level within which the population parameter is estimated to fall between a set of values for a certain proportion of times. The confidence level is the likelihood expressed as a percentage or a probability that a specified interval will contain the population parameter. So, the point estimate is a sample statistic used to estimate the exact value of a parameter. The mean is an example. Note 1. One of the major applications of statistics in estimating population parameters from sample statistics, for example, point estimate, a poll may seek to estimate the proportion of adult residents of a city that support a proposition to build a new shopping complex. Out of a random sample of 200 people, 106 support the proposition. In the sample, 0.53 of the people support the proposition. This value of 0.53 is called the point estimate of the population proportion. It's called a point estimate because it's an estimate consists of a single value or a single point. The confidence interval is essentially just a range defined by the confidence level within the population parameter. With the confidence interval, it's rare that the actual population parameter would be equal to the sample statistics. So for example, it is unlikely that if the researcher polled the entire adult population of a city, exactly let's say 53% of the population would be in favour of the proposition. Instead, a confidence interval is used to provide a range of probable values for the parameter. The confidence level is basically how confident you are about the probability. I mean, in most cases here you would want a 95% confidence level. It's the likelihood expressed as a percentage or a probability that a specified interval will contain the population parameter, which you can have an upper and you can have a lower limit. In statistics, the confidence level indicates the probability with which the estimation of the location of a statistical parameter is like to the mean. In a sample survey, this is also true for the population. A small sample size will result in a wider confidence interval with a larger margin of error. A high confidence level is ideal at 95%. So consider, for this reason, point estimates are usually supplemented by interval estimates or confidence intervals. Confident intervals are intervals using a method that contains the population parameter for a specified portion of time. So for example, if the researcher used a method that contains the parameter 95% of the time it is used, they would arrive at the following 95% confidence interval. The researcher would then conclude that 46% and 60% of the population supported the proposal. You have to consider error and bias. So assume that theta, the Greek letter, is the value of the population parameter that we're interested in. In statistics, the estimate is represented by theta. The estimate theta would rarely equal the actual population parameter theta. There is some level of error associated with it. So we define this error as the following formula. All measurements have some error associated with them. Random errors occur in all data sets and are sometimes known as non-systematic errors. Random errors can arise from estimates of data values, imprecision of instruments as well. This is errors in your methodology. An example of error and bias, when you read lengths off a ruler, for example, random errors will occur in each measurement as a result of estimating between which two lines the line's length lies. Bias is sometimes known as systematic error. Bias in the data set occurs when a value is consistently under or overestimated. Bias can also arise from forgetting to take into account a correction factor or from instruments that are not properly calibrated. Bias leads to a sample mean that is either lower or higher than the true mean. In relation to estimates and sample size, before beginning a study, it's important to determine the minimum sample size, taking into consideration the desired level of confidence, the margin of error, and a previously observed sample standard deviation. When, for example, the sample size is greater than or equal to 30, the sample standard deviation can be used in place of the population standard deviation. The minimum sample size needed to estimate the population mean is calculated from the following formula. But again, these can all be applicated from apps for sample calculation with formulas which you can get on the internet. The minimum sample size, n, needed to estimate the population proportion is calculated using the following formula. So sample size calculation, the important point, has to be known before you commence your study. Determining sample size. This is required to estimate the population mean. Before calculating a point estimate and creating a confidence interval, a sample must be taken. Often the number of data values needed in a sample to obtain a particular level of confidence within a given error needs to be determined before taking the sample. If the sample then is too small, the result may not be accurate or useful. If the sample is too big, both time and money are possibly wasted in the sampling process. So determining the sample size in the population mean, first consider the margin of error. And this is the greatest possible distance between the point estimate and the value of the parameter it is estimating. To calculate the margin of error, we need to know the desired confidence level and the population standard deviation. When the sample size is greater than or equal to 30, the sample standard deviation can be used to approximate the population standard deviation. Okay, to change the size of the sample error requires two variables that could be changed. And this could be the level of confidence or the sample size. The standard deviation you can't change. As the confidence increases, the margin of error also increases. So to ensure that the margin of error is small, the confidence level would have to decrease, and that's not a practical solution. However, since the standard deviation is often unknown, and the standard deviation of the sample from the previous sample, which is now greater than or equal to 30, may be used as an approximation to the standard deviation of the sample, now we can solve for the sample to see what would be the appropriate sample size. Note that the sample size must be a whole number, always rounded up to the next whole number. Don't use it with a decimal. See, the larger the sample size, the margin of error decreases. Very clear in this diagram. Sample of size, for example, at the peak, 2,401, margin of error 2%. Then we go down, sample size 96, margin of error 10%. So as the sample size increases, the margin of error decreases. The larger the sample, the less the margin of error. So let's review. Suppose the scores on a final exam are normally distributed with a standard deviation of 10 points. Construct a 95% confidence interval with an error of no more than 2 points. The solution would be as follows. Therefore, a sample size of 68, rounded off to the nearest whole number, must be taken to create a 95% confidence interval with an error of no more than 2 points. A college observed that students in a non-transfer level course only need a 6-week refresher course instead of an entire semester. If 10% of the students fall into this category, how many must the department survey if they wish to be 95% certain that the true population is within plus or minus 5%? The solution is as follows. Therefore, a sample size of 139 must be taken to create a 95% confidence interval with an error of plus or minus 5%. Now let's look at what are point estimates or estimators. A point estimator is a function that's used to find an approximate value of a population parameter from random samples of the population. They use the sample data of a population to calculate a point estimate or a statistic, and that serves as best estimate of an unknown parameter. An example, finding the average age of children attending a kindergarten, will be impossible to collect the exact age of every preschooler in the world. So a statistician can use a point estimator, the mean, to make an estimate of a population parameter. What are some of the properties of point estimators? Bias is one. And bias is defined as a difference between the expected value of the estimator and the value of the parameter being estimated. When the estimated value of the parameter and the value of the parameter being estimated are equal, the estimator is considered to be unbiased. The closer the expected value of a parameter is to the value of the parameter being measured, the lesser the bias is noted to be. Then you've got consistency. Consistency informs how close the point estimate stays to the value of the parameter as it increases in size. This requires a large sample size for it to be more accurate. A point estimator is consistent by looking at its corresponding expected value and variance. The expected value should move towards the true value of the parameter. Then it has to be efficient or unbiased. And this means it has the smallest variance of all the unbiased and consistent estimators. The variance measures the level of dispersion from the estimate and the smallest variance should vary the least from one sample to another. The efficiency of the estimator depends on the distribution of the population. So for example, in a normal distribution, the mean is considered more efficient than the median, but the same does not apply for asymmetrical distributions. When we look at estimators, there are two main types: point and interval. Point estimation is the opposite of interval estimation. Point estimation produces a single value. Interval estimators produce a range. A point estimator uses sample data. Conversely, interval estimation uses sample data to calculate the interval of possible values of an unknown parameter. The interval of the parameter is selected in a way that it falls within a 95% or higher probability, which again is the confidence interval, which we'll be discussing later. So common methods for finding point estimates are as follows. Finding point estimates, this is the process of point estimation, which involves utilising a value of a statistic that's obtained from sample data to get the best estimate. Several methods can be used to calculate point estimates, such as Methodist Moments or maximum likelihood estimators, MLE. Methods of moments, this was introduced in 1887 by a mathematician from Russia. It starts by taking down known facts about a population and then applying those facts to a sample of the population. It derives equations that relate to the population moments to unknown parameters, and you draw a sample of the population to be used to estimate the population moments. This produces the best estimate of an unknown population parameter. Then you've got the maximum likelihood estimator, and this attempts to find the unknown parameters that maximize the likelihood function. It takes a known model and uses the values to compare data sets and find the most suitable match for the data. So for example, a researcher may be interested in knowing the average weight of babies born prematurely. Since it would be impossible to measure all the babies born prematurely in a population, the researcher can take a sample from one location. Since the weight of preterm babies follows a normal distribution, the researcher can use the maximum likelihood estimator to find the average weight of an entire population of preterm babies based on the sample data. So examples of point estimates are: imagine you're tossing a coin, and every time you toss, you note down the result. For an unbiased coin, which means it has a head and it has a tail, and sufficiently large number of trials, you should get roughly 50% heads and 50% tails. But what if the coin is biased? For example, slightly bent or not as it should be? Then after a large number of tosses, you will discover that one of the sides appears more often. That means that the probability of getting heads is different than 50% for that particular coin. The point estimate is exactly that probability of getting the heads result. There are 4 different point estimate formulas. And I'm not going to go through all of them really, but just to mention here, you've got the maximum likelihood estimation, the Wilson estimation, the Laplace estimation, and the Jeffrey estimation. And each formula gives you a different result and should be used in relevance circumstances. So calculating the point estimates requires the following values: the number of successes, which means the number of heads you got tossing the coin, the number of times you did it, the trials, the number of times you tossed the coin, the confidence interval, which is the probability that your best estimate is correct within the margin of error, and the Z-score, calculated from the confidence interval. Point estimate equations, you can review them. I'm just going to flip through them. You can see them on the PDF version as well. Example, finding the point estimate. Determine the number of tosses, count the number of times that you got the heads, decide on your confidence interval, calculate the z-score. And you can use the following point estimate formulas. When we come to an activity, the confidence interval estimator, to construct a confidence interval estimator of the mean population, we use the following formula. The confidence level that we get is from a z-table. Step 1, to be more precise, we're constructing a two-sided confidence interval. So the example would be, you work for a company that makes smart hand phones, and your supervisor asks you to determine with certainty 100% the exact life of the smartphone. He tells you to take a random sample of 100 mobile phones. So what is the exact life of a smart hand phone made by this company? The sample evidence is you've taken 100 samples, the mean is 11.5 years, and the standard deviation for the sample is 2.5 years. So the answer that you provide is that you don't know. Your supervisor asked for 100% confidence, which isn't feasible. And as a consequence of that, because if you want 100% confidence, you've got to take a census. With a sample, you can never be absolutely certain as to the value of the population parameter. That's exactly why statistical inference is about using conclusions, estimates. The better answer would be here that you're aiming for a 95% confidence interval. And that's what the confidence interval would be. The better answer in relation to the interpretation, you're 95% confident that the interval from 11.01 years to 11.99 years contains the true population parameter, the mean. In 95 out of 100 samples, the population mean would lie in intervals constructed by the same procedure, the same number and the same standard deviation. And then you note the population parameter mean is fixed, it's not a random variable. Therefore, it is incorrect to say that there is an interval of 95% chance that the population mean will fall in this interval. So in example 2, the life of a refrigerator, the sample is that you've got 100 refrigerators. The mean is suspected to be 18 years and the standard deviation for the sample is 4 years. So you want to construct a confidence interval estimator of the true population mean at the end of each of these levels of confidence. The answer for this example is, if you want 100% confidence, not possible. 99% confidence, 16 to 9 to 19.0 years. 95% confidence, 17 to 18.7 years. 90% confidence, 17 to 18.6 years. 68% confidence, 17 to 18.4 years. And these can all be calculated with the appropriate calculators, which are all available on certain apps on the internet. So in summary, when using a sample, not the entire population, you cannot be 100% certain of population parameters. If you need to know the value of a parameter certainty, take a census. The more confidence you want to have in the estimator, the larger the interval is required. Traditionally, statisticians work with a 95% confidence. However, you should be able to use a z-table to construct a confidence interval estimator at any level of the confidence. Okay, that concludes this session in an introduction to the basics. There are 7 other parts to this basic statistics learn shop. And remember, it is just the basics. And you can get access to a lot of other information on some of the excellent YouTube videos. See you in the next session, and if you think this has been of any value to you, or any of the other Dr. Manny Learn shops, recommend them to your friends and colleagues. Thanks, see you soon.